In this video, we're going to go over the concept of related rates. And so we're going to start with this problem. Let y be equal to the function x squared minus 7x. So here we can see that y is explicitly a function of x. So we can say y of x or f of x equals x squared minus 7x. So when I ask to find dy dx, that means we're going to take the derivative with respect to x of both sides. And so when we do this, the derivative of y with respect to x is just dy dx, which is what we're looking for. And this is a function of x already, so the derivative of x squared will be 2x minus 7. And so this will be our dy dx. Now here, we're working with the same function. But notice that now I'm asking you to find the derivative of y with respect to t. So what this means is that then that y is a function of t. So that means that here, because y is given in terms of x, then x is also a function of t. And so we need to take the derivative implicitly. So when I have y equals x squared minus 7x, when we take the derivative with respect to t, I'm going to be taking the derivative with respect to t of y and the derivative with respect to t of x squared minus 7x. Now keep in mind that now x is also a function of t, so I have to take the derivative with respect to x implicitly. The derivative, with respect to t implicitly. So here I'm going to have dy dt equals, now x is not the variable, I'm not taking the derivative with respect to x, right? Like here, when I took the derivative of x squared with respect to x, I got 2x. But here, x is x of t, so when I take the derivative, I'm going to have 2x times the derivative of x with respect to the variable t. So I'm going to have times dx dt minus the derivative of 7x with respect to t, so this is going to be 7 dx dt. And so that will be our derivative. So this was done implicitly, since both x and y are functions of t. So having x and y here be functions of t is very similar to when we talked about in implicit differentiation about the ripple effect of throwing a pebble into the water. And so we noticed that there were circles, right, that were created when the pebble gets thrown in the water, and then those circles start to increase as time goes on. And so we talked about, when we did this section in implicit differentiation, what's changing. The area and the circumference are changing. So we talked about a few things. As time passes, the radius of each circle changes, the area changes, the circumference changes. And then how can we incorporate the concept of implicit here? So we said the area then becomes a function of t, the radius becomes a function of t, and the circumference also becomes a function of t. And if we go back to those notes or that video on implicit differentiation, you'll see we actually did a related rates problem in there. I just didn't call it that. We were just doing an implicit differentiation application. But essentially related rates is implicit differentiation, is the applications of functions when they're written implicitly. So going back to that example with the ripple, right, if say t after 1 second things are changing, what's changing? The radius is changing, the area is changing, and the circumference is changing. And then if 3 seconds go by, now the radius is larger. So you have, so I'm going to call it R1, R3 after 3 seconds, and then, and I'm just making up these numbers. So after t equals 7 seconds, for example, right now you're going to have the radius, whatever it is, after 7 seconds. And so the radius is increasing, the area then is increasing, and so is the circumference, right, around the circle. The area is the inside of the circle. So let's try an example. A different example than the one that was done when we did the implicit differentiation video. So let's try this one. A balloon is inflated at a rate of 20 inches cubed per minute. How fast is the radius of the balloon changing when the radius reaches 2 inches? So we want to know, with word problems, always focus on what you're being asked to find. What is the task? So here we want to find how fast is the radius changing. So when the radius reaches 2 inches. Another thing to note is that things here are changing as time goes on. So notice that the balloon is being inflated at a rate of 20 inches cubed per minute. Pay attention to the units. What kind of units are these? Inches cubed per minute? Inches cubed is a measure of what? This is a measure of volume. Right, so then that means, okay, so what's going on in this problem? I have a balloon is being inflated at a rate of 20 inches cubed per minute. So I'm being given a volume, the rate of change of volume. I want to know how fast is the radius of the balloon changing when the radius reaches 2 inches. So let's draw a little picture here of what's happening. So you start off with a balloon. Well, I'm not going to draw the balloon that's not inflated, but as you start to inflate it, it becomes bigger, right? So you're putting air in at a rate of 20 inches cubed per minute. And then as you go on, right, as time passes and you continue to inflate this balloon, what's happening? It's getting bigger. So, and it says it is a spherical balloon. So you have your radius and you're still putting air in at a rate of 20 inches cubed per minute. So that's a constant rate. And then, right, this keeps getting bigger. So it's kind of like our circle problem, but now we have a sphere. And so we want to know, okay, at the instant when the radius is 2 inches, how fast is the radius changing? So how fast is the radius moving? Right, so we're asking for essentially kind of like an instantaneous rate of change. So we want to know, okay, and that if you were able to take a snapshot of how fast things are changing, as soon as the radius hits 2 inches in length, how fast is the radius changing? So that is instantaneous velocity. So that means we need a derivative. So the derivative of what though? So let's see. And sometimes with these problems, if you have to read it 2 times, 3 times, 10 times, that is completely normal. Sometimes I read a problem 5, 6 times until I can get everything out of it. And it's always helpful to read it once you feel you're done with the problem, you're finished. Go back and read it again. Did you answer the question? So word problems are, the more you read them, the better. So if you find yourself, I have to read this over and over, like that is completely normal, and you should be reading it over and over until you get all the information that you need out of it. All right, so let's see. A balloon is inflated at a rate of 20 inches cubed per minute. So I know that that's a measure of volume, but it's given in inches cubed per minute. So what I really have then here, what I'm given or what I have is the rate of change of volume. So I'm going to say dV dt, right, because it's inches cubed per minute. So that's a rate of change. So it's 20 inches cubed per minute. How fast is the radius of the balloon changing? So that's what I want. So we want the rate of change of the radius with respect to time. So that's what we don't know, but we want to know when r equals 2 inches. So what relates, and this is why it's called related rate, and what relates, that sounded like an evil laugh, what relates the volume and the radius in the shape that we have? We have a sphere. So here we need the formula for volume of a sphere. I don't necessarily expect you to remember those formulas from geometry, so whenever possible I will provide them to you. But the formula for the volume of a sphere, if you don't remember, is 4/3 pi r cube. So this relates the volume and the radius in a sphere. So that is my formula. Now, one thing to note is we want to find the rate of change. So how fast is the radius changing when r is equal to 2 inches. So one warning that I'm going to put right at the beginning, oftentimes I put this warning at the end, but I'm going to put it at the beginning this time, is that if I put in r equals 2 right now, what's going to happen? I'm going to get 4/3 pi 2 cubed, right? So that's 8 times 4, so 32 pi over 3. What is this? So if I just start plugging in numbers, just because I have a formula and I have a value, does this represent anything meaningful to what we're looking for? And no, right? Because the question is, how fast is the radius of the balloon changing? Nowhere in here is asking me what is the volume of the balloon. What I just found is the volume of the balloon when the radius hits 2 inches, but that's not something I'm being asked to find. So this is not relevant, right? So be careful to not plug in your value right away, because we need to find the rates of change, and right now I have no rates of change anywhere. So this gives the volume, but we're looking for, we want rates of change. So don't plug anything in until you have taken the derivative. So that is my warning. So let's go back to our formula for the volume. How do I get a rate of change in here? Notice that things are changing with respect to time, so that means that v is a function of time, and so is r. It's kind of like that circle problem right up here. Things are changing as time passes. So here, as time passes, the radius is changing, the volume of the balloon is changing, the surface area of the balloon is changing. So we want to, with respect to time, so we want to get our hands on the rates of change with respect to time. So we're going to take the derivative with respect to t of both sides. So I'm going to have d dt of the volume equals the derivative with respect to t of 4/3 pi r cubed. So on the left, we're just going to have dv dt, and on the right, now here is our r cubed. Now remember, r is a function of t, so I really have r of t cubed. So I need, when I take the derivative with respect to t of this function, what are we going to need? We're going to need chain rule. So let's do the chain rule there. So I'm going to have, bring the 3 down. So it's going to be 4/3 pi times then the derivative of r cubed with respect to t. So that's going to be 3r of t squared times, by chain rule, the derivative of the inside, so r prime of t, but I'm going to write it as dr dt. And so now we can reduce. So our 3's cancel, so we're left with just dv dt equals 4 pi r squared times dr dt. And let's go back to our setup. We have dv dt, that's 20 inches cubed per minute. We're looking for dr dt when r is equal to 2. So this is the snapshot, right? The instantaneous. We're looking for the instantaneous velocity as soon as the radius has hit 2 inches. What's the instantaneous velocity of the radius? So we can put that in now. So I know dv dt is 20 inches cubed per minute equals to 4 pi r squared. We're trying to find it when r is equal to 2, and times dr dt. And this is what we're looking for. Now let me add my units in here. This is really 2 inches squared. So notice that I have 20 inches cubed here and inches squared here. So when we divide by inches cubed by inches squared, we're going to get inches. So the radius is a measure of length, so it makes sense that I should have just inches per minute. So let's figure this out. So I'm going to have 20 inches cubed per minute equals, what's this? 2 squared is 4 times 4. So it's going to be 16 pi inches squared times dr dt. And our goal is to solve for dr dt. So divide everything by 16 pi inches squared. So I'm going to have 20 inches cubed per minute divided by 16 pi square inches equals dr dt. So the reason that I have my units here is, again, so you can see inches cubed and inches squared will cancel, leaving us with just inches, which makes sense for a measure of length, the rate of change of length. And so my final answer is going to be 20 over 16 pi inches per minute is my dr dt. And we can of course reduce that. 4 goes into both of those, so it will be 5 over 4 pi inches per minute will be our dr dt. If you want to change it to a decimal, that's fine. Keep in mind here that the pi is in the denominator, so this does not become magically 5/4 pi. The pi stays in the denominator, so this is 5 over 4 pi. The whole thing is in the denominator, so this will be the rate of change of radius. Okay, so let's recap. So what did we do? So you're given a related rates problem. How do you recognize a related rates problem? You'll be given some rate of change, and you're likely are going to be asked for another rate of change. So a balloon is inflated at a rate of 20 inches cubed per minute. That's a rate of change. How fast is the radius of the balloon changing? So you're being asked for a rate of change. Let me change that to a lowercase. And when the radius reaches 2 inches. So we kind of try to picture the situation, what's happening. So you're putting air in a balloon, so the balloon is getting bigger. If, by the way, you have a full balloon and then somebody pokes a little tiny hole in it and it starts losing air, now my rate of change, my dVdt, will be losing air, so that will be a negative, right? Because then the volume will be decreasing at a certain rate. And so what do you have? What are you looking for? And then try to relate those formulas. The variables. I have V for volume and R for radius in a balloon. So what relates those variables? And so hence the related rates. So we need the formula. Once you have the formula, don't plug in anything at the beginning. Take the derivatives with respect to the variable needed, and then you start plugging in once everything is simplified, because now you're going to have rates of change. So everything that I just said, I kind of put it together in a little table to help you solve related rates problems. So let me put that in here real quick. So here's the kind of the steps that I would follow for solving related rates problems. So draw a picture with variables. So notice I'm gonna go through the steps and show you kind of what we did. So we have the problem, we drew a picture, and I did put variables. Notice that the radius in a sphere, the radius is what I can label. So put that as a variable. That's changing, right? It's not always 2. Don't draw a picture and put 2 in it, because the radius is not always 2. At 2, we're taking a little snapshot of what's happening, but the radius continues to change as time passes. So draw a picture with variables. And then the next thing is identify your dwatt dwatts. I know that my very technical terminology here, but that is essentially what we did here. Like, what do we have? What rate of change are we given? A d something, your dwatt dwatt. And I know 20 inches cubed per minute based on my units. Really, really, really important to pay attention to units in related rates problems. So the units is what tell me that I have volume. So inches cubed per minute. So I have volume is changing with respect to time. So I know that I have dV dt. And I'm looking for how fast the radius is changing. So now that I know that things are changing with respect to time, then this is going to be dr dt, right? Using my variable that I used in the picture. Once you have your dwatt dwatts, write an equation relating the variables in the numerators of your dwats. So that's what we did in this example, right? I had a dv dt and a dr dt. So the variables in the numerators are v and r. So volume and radius, and my picture is a sphere. So that's how I get my formula. Okay, how do I relate volume and radius in a sphere? I need the volume of a sphere. So write down that formula and then take the derivative implicitly with respect to the variable in the denominator. So that will be our dt. So you take it with respect to t, and then you evaluate at the specified value. So this is the very last step, is to plug in the specified value. You don't do it at the beginning, right? And even if you do, ask yourself, did I find a rate of change? No, right? So back to that problem, when my warning, if I just put in r equals 2, I get the volume. There's no rate of change here. The task was to find the rate of change of r, and if I just plug in 2, what I found was the volume of the balloon. I didn't find any rates of change. In order to find rates of change, you need to take the derivative. So that's why you want to make sure you plug in your specified value at the very end. So I'm going to leave you with an example. Try it on your own to set up at least to where you have the formula to step, which one? Step 3. Write an equation relating the variables in the numerators for this next example. And then in the second video, part 2 of this video series, we'll solve it. So our example is, water is being poured into a conical tank at a rate of 10 feet cubed per minute. How fast is the water level rising when the water in the tank is 3 feet deep? Assume the radius of the cone is half its height. So you have a conical tank and you have a rate given. You want to know how fast is the water level rising when the water in the tank is 3 feet deep. So go ahead and do step 1, step 2, and step 3 on your own and see what you come up with. So draw a picture with variables, identify your dwats, and write an equation relating the variables in the numerators. And then go on to part 2 of the Related Rates video series, and then we'll solve it together.